So, we get into a new topic today, having discussed the structure of the blast furnace, its construction, various accessories, then the burden material, etc. So, we now move on to discuss the physicochemical and thermal characteristics of an iron blast furnace. This actually is the center of the blast furnace discussion, because most of the fundamentals will be dealt here, and I will take you through the entire iron making process, give you the essentials, so that this will set the groundwork for dealing with more advanced phenomena as far as iron making in a blast furnace is concerned. So, most of the critical fundamental points will be discussed in today's lecture 5 as well as in the subsequent lecture 6, and as I said that this will put you in proper perspective in terms of gaining the fundamental knowledge with regard to the iron making, but it may not be a very comprehensive, but it will set the groundwork for dealing with subsequent topics or even more advanced level courses in an iron with regard to an iron blast furnace. Now, we have seen that the raw material, iron bearing material that we charge into the blast furnace, or the source of iron, is our hematite, and this basically is an indirect reduction, we call it, because direct reduction is the term when we use solid carbon to reduce iron. So, if I would have written instead of carbon monoxide gas carbon here, I would have said that this is a direct reduction by carbon. First we convert carbon into carbon monoxide and then carbon monoxide reduces. So, it is an indirect reduction, indirect gaseous reduction of iron hematite. So, various terminologies also be introduced. You just keep track of my lecture, so that you do not miss any of those, and this basically can be represented. So, this is gas. So, we will write all the equations like this, and this is solid, and then we have carbon dioxide. As I have indicated that it undergoes, of course, not in one step, but in several steps, but the essential overall reaction of that production of iron from iron ore can be represented like this. So, this reduction reaction, which proceeds in several stages, at elevated temperature in the blast furnace. So, the temperature here, as I have indicated, is about 500 degrees centigrade, and here it is about 1900 2000 degrees centigrade. We must understand the gas is very high in the combustion zone. So, this is the section of the bustle pipe. Today I have drawn it like this. In the last figures this was not shown here. So, this is the section of the bustle pipe which is going around the blast furnace, okay? And this is the tuer through which, and it is only shown on one side not to complicate the figure. And here we have a combustion, the raceway, and that raceway basically, so we write it at R, which stands for raceway, and here the temperature is 1900. So, the gas is at very high temperature, the solid is at very low temperature. We will discuss the thermal aspects more elaborately later on, but it is sufficient for us to note that as the gas rises up, okay, the gas temperature will progressively go down, because the gas will yield its heat to the descending solid, and the solid is going to progressively heat it up. So, therefore, even though we may be charging the iron ore or Fe2O3 at room temperature, these materials, as with progressive descent, the iron ore component or the iron bearing component will be heated up and will enter into intense hot chamber of blast furnace, as a result of which we can assume that we have a high temperature scenario, and also we have, as I have indicated, and we can get this information from Ellingham diagram also, that at such high temperature, okay, we will never get any carbon rich bath or carbon rich system, a system which is filled up with lot of excess carbon. We will never get carbon dioxide, because carbon dioxide is a phase which is relatively stable at lower temperature, close to room temperature, or maybe at very low temperature, okay. But more intense is the relative stability of carbon monoxide is much higher at higher temperature than carbon dioxide. So, at high temperature, so if you measure the concentration of the gas phase will be 100% CO near the tuer zone itself, but as it is rise up, then the reaction will take place, and the proportion of carbon monoxide and carbon dioxide in the rising gas column is going to change. And as I have indicated that we can have an off gas, that off gas will contain something like 20% CO. These are not sacrosanct values, they will depend on the practice, on the raw materials, and many other aspects which will come out in this discussion today, maybe 25% CO2 and then 55% nitrogen and so on. We must understand that nitrogen which is injected or which comes via the air phase is inert, it does not change significantly. So, there is only a dilution effect, air contains 79%, but the gas overall gas mixture which comes out, there the relative proportion of nitrogen gets, but the nitrogen remains conserved. Whatever mass wise, whatever nitrogen you put in comes into the furnace via the air phase is the same quantum of nitrogen which goes out, barring little bit changes here and there, maybe little dissolution and so on and so forth. But so we can expect that the descending iron ore which progressively gets heated up will be particularly in this part of the furnace which is relatively at high temperature, will be subjected to a temperature of about 900,000 1100 degrees centigrade, and also will be subjected to a gaseous environment which will be predominantly carbon monoxide. Now, in the blast furnace charging, we will see that we charge in layers. For example, we will have one layer like this which is our maybe limestone and iron ore combined, okay, and then we have another immediately below it is a coke layer. So, what happens, these layers are repeated. So, once the gas comes out, okay, the moment it reaches, it comes up passes through the coke bed. So, this is our coke and this is maybe iron ore and limestone. Then what happens is, because it is a high temperature region, because it is coke, even though some carbon dioxide is there here, as the gas is rising up, okay, it flows to the hot bed of carbon. What happens is that entire thing gets converted into carbon monoxide. So, this layer of iron ore which is there stacked up in alternate layers are progressively exposed to a very intense environment of carbon monoxide. So, that is what is we do the charging, so that whatever carbon dioxide has been formed because of the reduction reaction in the lower layers, that carbon dioxide in an upper coke bed can get converted into carbon monoxide, and then the one iron ore layer which is lying on top of it will be freshly exposed to 100% or a very intense carbon monoxide. And we know that if we have high temperature, we have lot of carbon monoxide. In that case, we can say that we can look at the Ellingham diagram and we will find that this reaction is indeed possible. Okay, there is no way. I mean, if you take lump of iron ore, you heat it up with carbon monoxide at 900 degrees centigrade, you will get metallization. It is thermodynamic reality. So, there is no issue that in a blast furnace when you charge iron ore, you will get iron. But the question is, what is the more important is, what is the rate of iron production? What is the quality of that hot metal that you are producing? Is it 50% iron or 80% iron or 90% iron? Because there are a lot of impurities along with such reduction reactions. We can also have co-reduction of various constituents, and they can manifest in the hot metal itself. So, there is no fundamentally speaking, it is clearly understood that iron ore subjected to a high intense temperature as well as a reducing environment will immediately get converted, spontaneously get converted into iron. So, production of iron thermodynamically is not an issue at all. Your ability to create a high temperature and an intense carbon monoxide environment is what is needed. But having produced those two environments, I think there is no question about that whether iron oxide will reduce or not. That question does not arise. It is a reality that iron will undergo spontaneous reduction. Now, we have several reduction reactions we can consider. Basically, we can understand that this layering one with regard to three different reactions. I will explain that. One reaction we can say is, we must understand that it is shown that the strength of the iron ore, oxygen is more, it is it is extremely easy to remove the first oxygen and convert Fe2O3 to Fe3O4. Then from Fe3O4 to FeO, it is little bit difficult. Then from FeO to Fe, it is extremely difficult. So, the little bit of carbon, so if I change my statement, I would say little bit of carbon monoxide will be able to reduce Fe2O3 to Fe3O4. More carbon dioxide is going to be needed to reduce Fe3O4 to FeO, and even more intense carbon monoxide is going to be needed to accomplish the final stage of reduction. So, therefore, we can understand that in the furnace, this will undergo reduction in the top part of the furnace, where temperature and carbon monoxide concentration is going to be small, because temperature is smaller. So, again I go back to my statement of Ellingham diagram, that at lower temperature carbon dioxide is more stable and higher temperature carbon monoxide is more stable. So, here we have more carbon dioxide and lesser carbon monoxide, and as a result of which I can get reduction of this, but certainly not reduction of this in the upper part of the furnace. These are certain corollaries which we can deduce on the basis of our existing our present knowledge of elementary thermodynamics and so on and so forth. Now, so we will not talk about the reduction of this to this, that is per se not an issue at all. Okay? Let us then consider this reduction reaction Fe3O4 plus CO. We should always write solid, even though I may not be writing, just to save on time, okay, that we have this reaction FeO, and this reaction needs to be balanced. I will not balance, I will not spend some time. So, carbon dioxide, which is gas, and then we have second reaction FeO. This needs to be looked at now to quantitatively explain. I have made my statement that iron ore will undergo spontaneous reduction qualitatively, but now I am going to show you, how do you quantitatively analyze the scenario. So, this is CO, which is gas, and then we get Fe plus CO2, which is gas. And we have third reaction we consider is the gaseous gasification reaction, carbon plus CO2 gas, and then this is equal to 2CO. Now, we can, if we assume the total pressure Pt is known to us, and for the sake of simplicity, Pt means the total pressure. So, the total gas pressure is going to be equal to partial pressure of carbon monoxide plus because there is no other gas involved here, a simplified analysis. Okay. Now, if Pt is known, then suppose it is 1 atmosphere, suppose it is total pressure is 1 atmosphere, CO plus CO2 combined. In that case, at any temperature or at different temperature, 700 degree, you can calculate for this ideal reaction, when you consider this is a pure solid, this as a pure solid, and you can calculate that what is the partial pressure of carbon monoxide, equilibrium partial pressure of carbon monoxide and equilibrium partial pressure of carbon dioxide. From the free energy versus temperature relationship, we know delta G naught is equal to minus RT ln K equilibrium. If you apply that to this equation, you will be able to find out what is partial pressure of carbon monoxide, what is partial pressure of carbon dioxide, no issue at all. So, you can calculate that what is percentage CO equilibrium, what is percentage CO2 equilibrium. This sort of a calculations you may have done in chemical thermodynamics course at the second year level. So, I do not have to do it, and the basis of this calculation is given the total pressure, you apply this delta G naught T is equal to minus RT ln K equilibrium, and where K equilibrium is nothing but PCO2 by PCO, having said that these solids are in their pure state, and then you find out. Similarly, if you apply the same logic, you can calculate for this. So, percentage CO equilibrium, and this reaction I have said 2, so it is 2, and then percentage CO2 equilibrium. Exactly the same procedure, we can do it here also. Percentage CO equilibrium 3 and percentage, all can be calculated. Having calculated these three, we now construct an important diagram. So, we will plot, and this can be calculated at different temperatures, because delta G naught value is a function of temperature. So, at different temperatures you are going to get different values, and if you plot this, then we get three different lines. Okay. One is this line, this is what you are plotting, temperature, and this is percentage CO in CO2 mixture. This corresponds to equation 2. This line corresponds to equation 1. So, this is basically FeO 2 Fe, and this is Fe3O4 2 FeO, and we have another line here which goes something like this, and this is corresponding to line 3. This is CO2 to CO. And this value, suppose if you consider arbitrary, about 1000 degrees centigrade, okay. Let us say this is 1000 degrees centigrade, and this value approximately corresponds to about 1. Percentage CO is 100. This is a 100% CO line. There is a percentage CO in CO2, that means there is 0 CO2, that is what it essentially implies. This therefore implies that if you have a layer here at 1000 degrees centigrade, then the moment the ascending gas, which may contain carbon monoxide and carbon dioxide, and nitrogen is inert, so that does not come into the discussion, there is no oxygen, oxygen has combusted right in front of the tuer. So, the gas which may contain carbon dioxide also, because of the reduction reaction taking place in the layer below, the gas, the moment it passes through the hot bed, which is this thick, it will try to attain, if the temperature is 1000 degree, an equilibrium with respect to 100% CO. But so a gas which leaves this coke bed is essentially at 1000 degree, 100 is 100% CO, but the moment it starts to interact with the iron ore, then what happens is the concentration starts to fall, because carbon monoxide is now going to be utilized in reduction and carbon dioxide is going to be produced. So, as more and more carbon dioxide is produced because of the reduction reaction, then the carbon monoxide concentration will fall down from 100 and come maybe, if it can approach equilibrium with respect to FeO, because we must understand that here at 1000 degrees centigrade we cannot have the higher oxides of iron ore, they have already been reduced in the upper part. So, only stable oxide at that, so we need not consider at this particular, because this environment, we must understand this environment, the range of carbon monoxide within this arrowhead essentially implies that this is going to be reducing the FeO, easily reducing FeO to Fe. So, if it reduces FeO to Fe, and this part, because it is above this line, any point above the equilibrium line, what does it indicate? That you have, for example, at any point of time you may have an K, the constant, not equilibrium constant is equal to PCO2 by PCO, that is what it is, the equilibrium constant for this oxide reduction reactions, equation 1 and 2. But suppose as the reaction goes on, at this particular point, the PCO and PCO2 is not equal to this, which is the equilibrium value here. So, suppose we say we calculate the K value, and K value corresponds to suppose this, and this K value essentially is going to be PCO2 by PCO. If I determine the ratio, that what it is, and I give it notation of star, which essentially means that this is the star, this is the location. This essentially means that whatever is the value of K equilibrium, which is this, okay, and this is the value of K. So, the moment K is greater than K equilibrium, okay, what does that indicate? That we have here, of course, you can see that the moment K is greater than K equilibrium, we are going to get oxidation, reverse reaction. So, the inverse of equilibrium constant, or we can say 1 by K is less than 1 by k equilibrium, because we want to calculate it is in terms of PCO, and then I will say if this condition, which is the same, because this is what it is, that the k equilibrium here, PC equilibrium constant here, because we have reverse reaction. So, if you say this k 1 by k is great, this is the same statement. So, I have reversed it. So, therefore, the taken reciprocal of it, therefore, the sign has reverse. Okay. So, it is the one and the same reaction. So, it is still reverse, and we can say that if this is 1 by k is greater than 1 by k equilibrium, in that case what happens, the reaction goes in the forward direction, that means the reduction takes place. So, k equilibrium is here, k equilibrium is here, that is equal to PCO2 by PCO. K is here, which is equal to PCO2 star by PCO. Now, we must see that the CO2 concentration here is maybe about 30%, but the CO2 concentration here is about 20%, it is more CO2. So, actually here k is less than k equilibrium, okay, because if you take the reciprocal of it, or k is or k inverse is going to be, because if you invert it, then it is PCO by PCO star by PCO2 star. So, 1 by k is actually now going to be which essentially will tell that the value of PCO. So, 1 by k is going to be greater than 1 by k equilibrium. This is satisfied in this particular domain itself. So, this essentially indicates that this environment, essentially what does it indicate, that we have more intense, more amount of CO in the gas phase than is required from the equilibrium of this particular reaction. So, if it tries to attain equilibrium with respect to this, the consumption of CO will have to take place. CO has to come down now from here to here, and this essentially means that CO concentration has to go down, move in this direction, and CO concentration will only go down provided CO is consumed and more CO2 is generated, and that essentially indicates that the reaction will go into the forward direction, and hence the reduction is going to be accomplished. And this is obviously, if you look at with respect to this, this concentration is much higher than this. So, therefore, we can say that if this environment can reduce FeO, this environment is going to be very, very intense with regard to the reduction potential required for conversion of Fe3O4 to FeO. So, it will automatically reduce Fe3O4. So, therefore, I have not considered any Fe3O4 here, because Fe3O4, the kind of CO concentration it requires, that is available much upward. So, I think that as the charge is descending down, Fe3O4 has already been converted in the upper part of the blast furnace itself. Right here Fe2O3 has been converted to Fe3O4, little bit lower Fe3O4 has been converted to FeO, and then right here we have only FeO left about 1000 degree. So, this line at 1000 degree, therefore, if you take the value here, this is something like 70% CO, and this is about 100%. So, a region here in the blast furnace where you have alternate layers of coke and high temperature like 900, 1000 and 1100 degrees centigrade. So, the carbon monoxide concentration is going to fluctuate between 70% and 100%. The moment it goes through the carbon bed, it will attain 100% CO configuration, and then once it touches the iron ore, it starts to flow through the iron ore particle bed, then what happens is the carbon monoxide concentration goes down and it tries to attain here. Whether it reaches equilibrium or not, that is a different issue, but once again the gas now contains more carbon dioxide, or somewhat more carbon dioxide. Next layer is again a coke layer. So, the moment it comes to coke layer, then what happens is it tries to attain equilibrium. So, the concentration in that particular range keeps on fluctuating between these two, and that is how we create, by charging alternatively, we create a very intensely reducing atmosphere in the blast furnace, which facilitates the reduction of FeO to final stages of Fe. And as I said that, so we can understand that this sort of an environment, because it is a coke packed bed, we have layers of coke, high temperature. So, it is clear that iron ore will have to go through this particular regime of CO concentration, and therefore, even though I have assumed that Pt is equal to 1 atmosphere, which may not be true, even though I may have assumed that Fe3O4 and FeO, they are all pure phases, which may not also be true, but this can be taken as a guideline to conclude that iron ore which is charged into the blast furnace, which passes where there is a combustion zone, generation of carbon monoxide, excess of carbon, high temperature, we can see that even at a first hand approximate reduction based on our thermodynamic considerations suggests that iron ore will undergo reduction and produce iron. Since the temperature, once iron is produced, and as we have higher temperature towards the lower part, and as the charged material further descends, it is also understood that Fe solid thus produced from iron ore can undergo liquefaction or melting, and thus gives rise to FeL because of the intensely high temperature which is prevalent. So, conversion of solid iron into liquid iron is also not a limitation. So, the more we have charged Fe2O3, there is no doubt that in such a shaft tall furnace we will be getting hot metal in the liquid state, okay, which contains predominantly iron. But as I have said that now we can given that we can produce iron, the question is at what rate iron is going to be produced. This is of the crux of the problem, because on that will depend on how as a business proposition iron production is going to be attractive, and also what should be the hot metal composition that we are going to get. Is it going to be pure iron? Is it going to be iron with lot of silicon, and so on and so forth? What should be the slag rate? And as I said that this will depend on mostly the kinetics will depend also quite a bit on the characteristics of the raw material and the burden material that we have seen earlier. The knowledge of burden material preparation that will come handy in terms of understanding the kinetics. So, the rate of production of iron is far more important, and we have to apply the engineering fundamentals so that for a given amount of ore treatment in the blast furnace, we can produce a ton of hot metal as economically as possible without impairing the environment to a large extent. So, we have to do it environmental friendly, we have to make money, we have to spend less resources, and then we have to produce as much as possible, because we have to sustain, the producers has to sustain competitive market. So, let us look at the kinetics of iron ore. How does the iron ore undergoes reduction? So, it is a gas solid reduction basically. So, again I will not dwell on the reduction of Fe2O3 to Fe3O4, I will not dwell on Fe3O4 to FeO, but the final stage of reduction, which is the most critical, and which that's what I can demonstrate, that this is the final stage. So, this is, suppose I take a spherical and we must understand that there may be by the time it has reached. So, this is our 900 to 1000 degree centigrade region of the blast furnace. Okay. So, somewhere here I would say lower stack region. So, this is a basically this should not go that high. So, I would say that this is the stock line. So, we have layers of. So, that is what it is we have been charging material. So, this is our basically the layered charging, that is what I say. Okay. Blue one may be coke, and then this may be iron ore and limestone. And this is the lower stack region, and where we have basically this is the reaction which is taking place here. So, by now at any instant of time in this particular region, what we can see, what we can expect, that when complete reduction has not taken place. So, if you have taken an iron ore, a spherical shaped iron ore particle. If it has undergone complete reduction, everywhere it is going to be iron, but we are not considering that scenario. Reduction is not yet completed, we are somewhere here, okay. So it is partially completed, and in that partially completed, if we take a sphere out, section it, look it under microscope, what we are going to see? We are going to see that, look, we have FeO which is present here, everything has undergone, and it is Fe which is there. These are the two phases only that is that can stay here, other oxides are not possible at all. Now, this particle, the solid particle, is subjected to now ascending gases, and that gas has CO2. The layer which is in immediate contact with the solid, there may be CO concentration higher, but as the gas goes up, maybe here the CO concentration is going to be smaller. So, that is what I have written, that this CO2 ratio is not 100, neither it is 0, it is in between some value. The gas goes, and how does the reaction takes place? So, we have, as you have know from our fundamentals of solid liquid heat and mass transfer, that around the solid we are going to have a boundary layer. Okay? So, the carbon monoxide has to penetrate the boundary layer, make itself available at the surface. So, carbon monoxide, once it is this dotted blue line is my boundary layer, and this is my concentration boundary layer, CBL, concentration boundary layer. So, the gas will penetrate through the reducing gas, CO is going to penetrate through the boundary layer. It has reached the iron interface. This is the edge of the boundary layer, concentration boundary layer, and this now represents a gas solid interface. That is what is this basically. There is a gas solid interface, but this reaction FeO plus CO does not take place here. The gas has to go inside, diffuse through or get transported through Fe, it can reach here, and then only it can see FeO, and therefore, this reaction is going to be possible at this particular. So, if there are cracks or pores in because during the reduction process, as we have seen, that there are large number of cracks etc. will be developed because of changes in the density of the various phases, metallization, their densities are not identical, because of thermal loading in the furnace itself, that it is being subjected to different thermal environments, because of abrasion maybe with the surrounding particles around. Such cracks are going to be, because solid state diffusion, if it is a very dense material, then in that case the diffusion is going to be a very, very slow process. So, gas basically goes through these pores, which we call as a pore diffusion. So, even though there may be a bulk, so there may be several pores, and those pores may be connected, short circuited, and through the pores predominantly the diffusion can take place. So, the gas from the gas solid interface will now move through the solid layer, Fe layer, then reach the interface, which we call as an FeO gas interface, and at this site this particular reaction is going to take place. So, the chemical reaction per se, which I have represented here, does not take place as such. There are mass transport steps involved in it, and that mass transport step, number one is the boundary layer transfer, number one is transfer across the solid layer, and then only this reaction can take place. So, these are called forward kinetic steps. So, there are two forward kinetic steps: transport across the boundary layer, transport through the solid Fe layer, then the chemical reaction, and then carbon dioxide has generated. That carbon dioxide must now come back or flow in the reverse direction. So, there are transport steps: carbon dioxide transportation through the solid Fe layer, carbon dioxide transportation through the boundary layer. So, two forward kinetic steps, one chemical reaction step, and one or two backward kinetic mass transfer steps or transport steps. These altogether 5 steps which I have just now, they determine the rate of the process collectively. But Of these 5 steps which I have just now mentioned, 4 are mass transfer steps, one is the chemical reaction step. Okay. So, the mass transfer may be rate controlling. I hope you all know that what is the rate controlling means, it is the slowest kinetic step, or chemical reaction can be slow rate controlling. If it is chemical reaction rate controlling, we say it is chemically controlled. On the other hand, if mass transfer is slow, then we say that it is transport controlled process. Now, of the 5 steps, one may say that look, essentially fundamentally speaking, there is one mass transfer step could be rate limiting plus the chemical reaction. When both mass transfer and chemical reaction both influence the rate of the process, then we say it is a mixed controlled process. On the other hand, if we say that of the 5 steps, only the boundary layer transport is important, then it is a transport controlled process, or the reduction reaction is actually transport control, and in that case all other steps can be taken to be virtually at equilibrium, including the chemical reaction which occurs at the FeO gas interface. So, now we know, we can now apply the first, say we say that of the 5 steps I will write 1, 2, 3, 4, 5. So, this is regarding transport of carbon dioxide. Okay. This is transport of carbon dioxide through the boundary layer. This is transport of carbon dioxide through Fe. This is chemical reaction CHR. This is transport of CO through concentration boundary layer, and this is transport of CO through Fe. In short, I have spoken enough on this kinetic steps, so I need not have to elaborate anything on the board. So, these are the 5 steps, and if I say that let us make a supposition that this and this determines the rate, then we say that this per se do not exist for us, they are relatively much faster. Okay. So, we can now derive an expression for rate, and if we assume that rate of, for example, if we assume that the rate of reduction is first order with respect to carbon monoxide concentration, then we will say that the rate of reduction is equal to the rate constant multiplied by concentration of carbon monoxide raised to the power 1. Similarly, mass transfer is also, we can say the rate of the mass transfer through the boundary layer can be the concentration difference between the two, that is what can be taken, okay, as the driving force, and then we can take a mass transfer coefficient, which is some sort of an expression of the rate constant, and then if these two processes are taken to be, and then we can have an overall, these are all heat and mass transfer course fundamental. So, we can say the overall rate constant inverse is reaction rate constant plus 1 by Km. That is the standard derivation that we can do, and the rate of reaction, provided the chemical reaction is first order, can be given in terms of CCO bulk, where CCO bulk, this derivation is not important for us, this can be derived, they are available in textbooks, they are available in internet, and you should be able to. Now, if you consider this also, this also, obviously the definition of overall rate constant will change. Okay? That is by far not the motivation here, but what I mean to say is that the rate of reduction reaction is a. So, if K overall, and we all know that this overall rate constant and this bulk, this is the bulk concentration means it is outside the boundary layer concentration. So, higher is the concentration of carbon monoxide, the rate is going to be much larger, and that is why we see that there is an increasing effort to inject, as I have indicated and you must have noted when we are talking about feed material to blast furnace, and there are gaseous injectants like we inject natural gases, and we inject some kind of a liquid petroleum gases. So, all this contains carbon monoxide and hydrogen. So, as a result of which, by injecting in the lower stack region more carbon monoxide, what we are basically doing? We are basically increasing the carbon monoxide concentration, bulk phase carbon monoxide. That means the particle is now going to be surrounded more by carbon monoxide than it used to be alone in the absence of these injectants. Okay? And as a result of which, what happens? We will see that the rate of the reaction is going to be enhanced as far as. Now, this overall rate constant, there is a mass transfer coefficient is given here, and this I think in terms of proper unit there has to be a surface area also which will come into the picture, okay, and depends on what units. So, if you try to do just the kg moles per second, in that case you will see that there is a the interfacial area also which will come into the picture, and that interfacial area means this interfacial area. Okay. The mass transfer rates, when you calculate the rate constant, mass transfer coefficient, and then you have the mass transfer rate itself. The mass transfer rate I dot say n dot CO across the boundary layer, one can write as Km A into delta C. Delta C is across differential concentration of carbon monoxide across the boundary layer. A represents the interfacial area and C represents. So, therefore, we can see that because this the surface area comes into the picture, similarly the heterogeneous chemical reaction also takes place on the surface itself. So, therefore, the surface area has an important parameter, and that is what we see, that when you have sinter particles like this which are joined together, okay, maybe rather than having a lamp, what we have basically done, we have basically created more surface area, and as a result of which we have been able to get more reduction or a faster rate of the reduction. So, by controlling temperature, because the chemical constant, chemical reaction constant, rate constant is a function of temperature, it follows an Arrhenius type of rate law, as you all know. Okay. And then we have the mass transfer theory tells us that the net rate of transport has also something to do with the flux becomes is equal to Km into this. So, this rate of reaction that maybe we have calculated is per unit area, actually, that you must remember, per unit area of the reacting surfaces, kg moles per meter square per second, that is the unit. But when you multiply it the rate the rate of the reduction rate of reaction with the surface area, then we will get kg moles per second, same as that in this particular unit. So, the temperature is an important parameter, surface area is an important parameter, bulk concentration is an important parameter, and this sort of stack injection phenomena, etc., they have actually come by analyzing the theory of the reduction process, okay, the kinetics of the reduction process, which tells us that indeed the carbon monoxide concentration in the gas phase, or even hydrogen also is going to be creating an intensely reducing environment within the stack region, facilitating a faster rate of reduction of iron ore. Now, alternatively, one can also do laboratory scale experiments, okay, and laboratory scale experiments, for example, can, if this is Ri and this is Ro, suppose, in that case we can say that the rate fraction converted, fraction reacted or fraction converted F, we can say this is initial oxygen present by definition, final oxygen present in the ore and then initial. It is at once clear to us that the moment a reduction reaction is completed, then what happens is, get some chalk, reduction reaction, then the final oxygen becomes is equal to 0, okay, and as a result of which what happens, if you look at that expression now, the final oxygen is 0, there is complete reduction has taken place, so it becomes is equal to 1. So, 1 means if this value is 1, that means complete reduction, if this value is 0, that means there is no reduction which has taken place. Now, this also can be converted, because the materials have this part of materials and this part of material has stoichiometry. From stoichiometry we can correlate with the volume, that how much of oxygen is going to be there. So, this equation expression can also be converted in terms of initial oxygen, which can be taken to be is equal to Ri R0 cube minus, and R0 cube where from it has come 4/3 pi R cube, okay, that formulation. So, it is a measure of the volume and Ri cube divided by R0 cube, okay. So, therefore, 1 minus Ri by R0. We must understand that Ri is changing as a function of time. So, therefore, f is also changing as a function of time, and f therefore, is a function of time, and if you say that the rate of change df over dt, that represents the rate of reduction. Is a measure of rate of reduction. You can understand that faster is the movement of this interface, more is the reduction efficiency. Okay? So, the reduction efficiency can be calculated based on, and how do you know that we can take pellets out in a laboratory scale experiments, which is very easy. Taking a pellet out from blast furnace, spherical pellet out from a blast furnace is going to be very, very difficult. So, we can take out, we can subject, change CO2 values, different values of CO2, subject it at 900 degree, 1000 degree, 1000 degree, 1100 degree centigrade. Then as a function of time, we can take out the pellet and we can dissect the pellet and then look it under a microscope to find out the interfacial area, and thereby we can measure the Ri value through microscopic study. This sort of a scheme that I have written, where the reaction front at a time t is equal to this, at another time is equal to this, where the reaction front is parallel to the, or maintains the same kind of a contour as the initial shape of the particle, we call it a topochemical model of reduction. So, adopting a topochemical model of reduction, taking a spherical geometry, we can see that it is possible for us to find out that what is the rate of reduction. The rate of reduction can be calculated theoretically also, and then we can compare the two, because I have ignored 3 in order to find out on the basis of 2 steps what is the rate of the reduction. Does this reduction matches with the experimental reduction rate? If they matches, that means these 3 other steps are truly not useful at all as far as reduction, they may be considered to be at infinitely fast. Okay? So, therefore, we can do a theoretical study, we can do an experimental study, and we can find out that how, on what parameters the rate of df dt changes, okay, as a function of time, increasing temperature, increasing carbon dioxide. Typically, we would say that if a phenomena is mass transfer controlled, and this I think you all know, the stirring is going to affect, because this mass transfer coefficient has very strong dependence on stirring. So, more is the flow, and mass transfer of course takes place because of concentration gradient, that is the driving force. Okay. Everything remains same. If the rate of reaction changes with stirring, then we can conclude that the mass transfer is playing an important role. Suppose I increase the stirring and observe there is no change in the rate of reaction, then I will consider that for that particular reaction mass transfer does not play any significant role. Same can be said, a similar statement can be made if we say the temperature. Suppose we increase the temperature and we find that the rate of reaction is not changing, then we can say that chemical reaction per se cannot be the rate limiting kinetic step or slow kinetic step, because we know with changing of temperature the rate of chemical reaction increases as per the Arrhenius rate law. So, thermodynamically it is feasible, and kinetics also tells us that it essentially tells us that how we can derive expression on the rate and understand that what are the factors that this diffusion, for example, that is the reason that why we want the pellets not to be too dense, but because if it is dense, in that case gas will find it, because the reacting interface is receding as a function of time, it is going inside and inside, and the path of diffusion is increasing as a function of time. So, if you make already this not friendly to the gaseous phase, in that case there will be difficulties in what you call for the gas to penetrate inside. We also know that, as I have indicated that mass transfer depends on the flow, for example, and in this particular case what happens is the gas solid contact time is very, very important. Okay. So, this environment, there is a tendency for the gas is moving at an enormous speed here. So, the contact time is small. If the contact time is small, that means the gas solid is exposed to carbon monoxide concentration for a shorter duration of time. But if you can slow down the gas a little bit, okay, slowing down the gas will reduce the mass transfer coefficient, but at the same time it will increase the carbon monoxide concentration around the particle for a longer duration of time. So, by if you can, for example, apply a high pressure here, relatively high pressure, maybe 1.5 times or 1.75 times the atmospheric pressure, and slow down the gas a little bit. In that case, what you are essentially doing is you are subjecting the ore particle to a more intense environment of carbon monoxide. So, the particle size is important, as you can see here, that, and of course, we want the gas which is coming here to be travelling all through the gas. If the permeability of the bed is not uniform, then the gas will be channelized. Suppose if there are too many particles here and the particles are loose here, or the particles are bigger here, particles are smaller here, the gas will find a path of least resistance and will flow, and as a result of which no reduction is going to take place. So, all these features of iron production that we theoretically describe are actually ingrained in the corresponding theory, and from this we can get useful insight of the operation in the blast furnace process. We will continue with this discussion.